A small smooth ring R of mass m is threaded onto a light inextensible string. One end of the string is attached to a fixed point A, and the other end of the string is attached to the fixed point B, such that B is vertically above A and AB is 6A. And we can see all of this in the diagram. The ring moves with a constant angular speed omega, as indicated in the diagram, in a horizontal circle with center at A. The string is taut and BR makes a constant angle theta with the downward vertical as shown in figure 2. The ring is modelled as a particle. Given that tan theta is 8/15ths, we want to find in terms of m and g the magnitude of the tension in the string. Before I do anything else, I'm going to deal with the angle. So we were given the angle that theta, which is this angle up here, tan theta is 8/15, so that's the opposite over the adjacent. Now, using Pythagoras, or knowing the 8/15/17 triangle, we then know that the hypotenuse is 17, and that tells me that sine theta is 8/17, and that cos theta is 15/17. We're going to need that, and of course you could have done that using your calculator. So let's consider R is here, and we were told that the mass was m, so the weight mg will act in this direction. If we just continue that up, this angle here would be theta. The tension in the string will be the same throughout because we're dealing with a ring, so we have tension there and there, which I'll just call T. Now, if we look at the vertical, we will get that T cos theta, which is the component of this tension in this direction, would be equal to mg. If we look horizontally, then T plus T sine theta, so that's the T here, and the component of the tension here, which is horizontal, that must be equal to mr omega squared. Now in part A, we're finding in terms of m and g the magnitude of the tension in the string, and we can get that directly from the first of our two equations. Let's call them 1 and 2. So for part A, 1 is going to give us 15t/17 is equal to mg, and therefore t is equal to 17 mg/15. We now want to find omega in terms of A and G. So we can use T plus T sine theta is equal to mr omega squared, which was our equation 2, which we got from the horizontal components. Now we know that T is 17 mg/15. And then here we have 17 mg/15 times sine theta, which we said was 8/17. And that's going to be equal to mr omega squared. But we can work out r. So we know that this is 6a here, and the radius would be here. So tan theta would be equal to the radius divided by 6a. But we know that tan theta is 8/15. Therefore r is going to be 6 times 8a, over 15, which is 16a over 5. So we can bring that down to here. Let's do some simplifying here. So we've got those will cancel out there. So we have 17 mg over 15 plus 8 mg over 15 is equal to m. Now we've just said that the radius was 16a over 5, and then we have omega squared. So the left hand side there is 25 mg over 15, and the right hand side is 16 ma over 5 omega squared. We can cancel an m out, and over here divide top and bottom by 5, and we get 5 over 3. So 5g over 3 is equal to 16a over 5 omega squared. And that means that omega squared is going to be 25g divided by 48a. So omega would be the square root of 25g over 48a. Now, in the mark scheme, that's given as 5 over 4 root g over 3a. So the square root of 25 being 5, which is how we get the 5 here. Remember that 48 is 16 times 3, and square root in 16 gets you the 4 here.